Our first presentation for this afternoon is on asset integrity, corrosion management, and scale inhibition. And the title is The Use of the Electrical Resistance ER Probes for Monitoring Internal Corrosion in the Oil and Gas Industry. Our speaker is Henry Leon, and we read his bio earlier. So, Henry, the floor is yours.
Thank you. Hello, good afternoon. Welcome back after the lunch break. In today's session, we have been talking about, and we will keep talking about chemical injection. And I think a key element is to make sure that the chemical products that we inject, they are doing their job, as we briefly explained earlier today during the panel discussion. That's why I thought it would be a good idea to present one technique to monitor the efficiency of the chemical products that we inject. That's why I came across with this presentation, use of electrical resistance probes for monitoring internal corrosion in the oil and gas industry. The content that we will discuss today to learn more about the ER probes is electrical resistance probes and its selection, advantages and limitations of ER probes, location in the system, interpretation of ER probes data. Finally, we will have maybe 5 minutes for questions and answers. I wanted to share my experience that why I came across with this topic that might sound simple. But in my experience, although for me this is quite familiar and easy to understand, I have came across with several operators, colleagues, friends, and they have no clue on how to use ER probes. They are coming from the design, they are there, they are installed, and after a couple of years, operators, they just stop using them because they don't know how to replace them, they don't know how to get information from them, they don't know how to interpret the information if they are able to get some info out of ER probes. And I realized that this might be a common issue, and it's an opportunity to share my knowledge with the audience and hope improve operations within our assets. So the first question that we need to ask ourselves is, what do we want and what can we do for monitoring, for corrosion monitoring? And then to answer this question, we need to think about, okay, do we want to do direct monitoring or indirect monitoring? Direct monitoring that provides us with the capability to measure corrosion rate by means of metal loss. So we can have a number, millimeters per year. Indirect techniques, they provide information to assess parameters that they might be influenced by corrosion rate, or they might influence corrosion rate. For example, water chemistry. When we check water chemistry, we can read the pH, or pH. Definitely pH will have an impact in the corrosion rate. Usually, the lower the pH, the higher the corrosion rate. But another example of indirect monitoring is iron count, because the higher the corrosion, the higher the iron count will be in our water chemistry. So if we don't have the possibility to install corrosion coupons or corrosion probes, because maybe we have limitations to install access fittings, at least indirect techniques, they can give us some information. Another approach or another way to look at this is what kind of technique do we want to use, intrusive or non-intrusive? Intrusive, we have the limitation that we need to penetrate into the system to get direct contact with the process. So we need to be into the pipeline, process piping, or the vessel. There are non-intrusive techniques like ultrasound that you can get information about wall thickness loss from outside of the process without all the safety issues associated to intrusive techniques. Another way to think about this is, okay, what type of media do I have? Because some of you might be operating assets that they are gas producing or oil producing, or you have, as part of the production process, water, produced water. So there are tables that might help you to assess, okay, what type of process I have in my system, and the expected degradation mechanisms. That's very important. If you have no clue what to expect, try to get support from a professional, experienced people in corrosion to identify your expected degradation mechanisms. Because it would be a pity that you invest a lot of money, for example, installing corrosion coupons or corrosion probes to try to assess hydrogen embrittlement. It's not going to work. You need hydrogen probes to assess hydrogen embrittlement. Therefore, it is important that from the early beginning, you have a clear picture of what's your system. In this table, I only want to highlight, as you can see already in green, that electrical resistant probes, they can help you in most of the media that we have in oil and gas production. Those are water, gas and liquid, oil and oil multiphase, and gas plus water. But they can't be useful in every, to assess all the degradation mechanisms. They are useful for two main groups. One of them, uniform corrosion, and the other one, flow-assisted damage. Later on, we will understand the reason of this, and it's because of their working principle. So, speaking of working principle, with electrical resistant probes, what we do is that we correlate the resistance of a metallic element that is in the probe. And because when you can imagine this situation like a highway. If usually you have two lanes to pass through, and one of them is closed, you will have higher resistance to pass through that highway. The same happens with electrons in metallic pieces. The smaller they are, the more difficulty electrons will have to pass through. So you will reach a higher resistivity or resistance. Therefore, with some math, you can get a reading from the handheld device to know, okay, what is the remaining thickness of this piece of metal in your probe. And eventually, you will be able to correlate two readings, you need at least two readings to have corrosion rate. We will come into more details later on. And because of the working principle, they can't be used everywhere. So they need to be in touch with water, for example. They can't be used when we have iron sulfate. We will see more about it later on. Usually what we have inside the system is this part of the probe that's directly installed in the process, and we have a handheld device giving us the remaining thickness of the equipment, of the probe, sorry. So the more sensitive, they are thinner, and the more robust, they are thicker. And the mass loss of these probes, it will come from corrosion loss or erosion or both of them. So we can use ER probes to assess corrosion, erosion, and erosion corrosion. We have several types of corrosion probes from the geometry point of view. One of them is the cylindrical elements. They are the thicker ones, more robust, and they can last longer in the system. The element is welded directly to the probe, and from the integrity point of view, they are very reliable. And they have a large area. That's why they can last longer in the system, because the probes, they are made out of a material that is almost the same, or some cases the same, as your process piping or equipment to be monitored. Because of the large area of this geometry, they are less susceptible to iron sulfate deposits. And they can be used in large range of pH, so practically in the whole range between 0 and 14. And you can use them up to 260 degrees in your process. There are also several alloys available for us. And this type of probe, the strip type, it's very sensitive. It's very thin, as you can see in the picture. This one, you don't want to use it where you have high corrosion rates. You want to use it when you have low corrosion rates. But we will also learn in a couple of slides how to find the balance between high corrosion rate and getting an accurate reading on time. This one is not suitable when you have fluoride ions. And most of them, they have a Teflon lining that can help to withstand more aggressive conditions. And we have larger alloys available for this type of probe. The third type of probe that you can find, they are flush elements. So they are convenient when you have pipelines, when you are planning to run cleaning peaks or intelligent peaks quite often, and you don't want to have to retrieve the probe every time that you're going to run a tool or a cleaning peak. So they are just flush to the inside diameter of the pipe. Okay, this is where, up to now, most of the information you could find it in the website of most of the suppliers. But this part, it's where I hope I will help you more. I told you that you need to find the balance between how long you want to have this probe installed and the response time. I will give you one example. If you're in a refinery and you want to make sure that your feed is not containing high levels of chloride, or your desalter process is not working properly, or the top of the distillation unit is not working properly, or the corrosion inhibitor is not working properly, you want to have a corrosion probe that has the shortest response time. Unfortunately, you will have to sacrifice the time that you can install that one. So for this type of processes where you need quick reaction and you need to know almost like a few minutes after the offset is taking place or changes in the corrosion inhibitor injection is taking place, for sure you will have to use this type of probes, the thinnest one. And for this type of probes, you might have to exchange them maybe every 6 weeks or 3 months. The range between A and B, as you can see here, they might last 2 years, 1 year, and if you're coming in this range, meaning that you have a high corrosion rate and you also need a short response time, you will fall into the range C-D, meaning you will have to change that probe every 3 months or every 6 weeks. And this is not coming only from the suppliers. This is information that I have back up from real situations. And for some people, it might sound strange. Okay, like every 6 weeks, I need to change this. It's necessary. In refineries, for example, it's a no-brainer. They know that they have to replace these probes in a few locations, not all of them. Some other locations, you are happy to have a response time of 2 or 3 days, and you can replace them every 2 or 3 years. How to do this? Okay, when you are selecting corrosion probes, you need to have a clear understanding, or at least a guesstimation of your expected corrosion rate, because that's the first parameter that you need to use to come here at the top of this graph. And then you also want to have information from a process, like, okay, how quickly do we need feedback from the corrosion probe? Do we need feedback in hours or days? And then you will have to do the exercise, okay, if you follow the green line, in case that you have a 10 MPY corrosion rate expected in your system, you can see here the different scenarios. For the state-of-the-art corrosion probes, micro core, you can have a response time of 10 hours. If you go to another one, the F40 type, you can have more than 110 hours waiting time for an unstable reading. And if you go to the thickest one, that they can last 2 or 3 years, it will take more than 1 week to have a stable reading. So this is why you need to have more information about the process and what do you want to get from this corrosion probe. Advantages. This technique allows to have continuous monitoring of your process, quite interesting in a refinery, corrosion inhibition optimization projects. You can identify offsets in the system, and you can, if they are online in your system, you can identify the exact time where something happened, okay? They can be used in almost any environment in the oil and gas processes. Yeah. And you can have, you can get results without retrieving the device. That's different story compared to corrosion coupons that you need to retrieve them to be able to get information. This technique is very useful for monitoring and determining corrosion inhibitor additions, as I already explained, because if you have the thinnest type of probe, you can batch or you can inject your corrosion inhibitor, and you can notice the change in a couple of minutes or hours. You don't have to wait weeks or months if you are doing this with corrosion coupons. Only one measuring device is needed, and the probe can be installed in the system until the end of the operational lifetime. Disadvantages. You need special staff and investment because the equipment is more costly than corrosion coupons. And as I said at the beginning, because of lack of knowledge and personnel with expertise, some operators, they are not using them. So you need to invest in your personnel to be able to have useful information. They are not recommended where you have H2S corrosion, as I said, because of the iron sulfide formation. You can't use it in liquid metals or some conductive molten salts. It's susceptible to temperature changes. And as I said already at the beginning, this technique can be used mainly for uniform corrosion and velocity influence degradation process, because you can't assess the pitting, for example. MIC, microbially induced corrosion, you can't assess that one with corrosion probes. Yeah, in some cases, corrosion rate, depending on the selection of the corrosion probes, can take a lot of hours or days to have a reading. And you can't have any information about degradation mechanisms from the visual inspection. Big difference compared to corrosion coupons. I already explained this one. Also temperature. Yes. And in some processes, you might be interested in using them temperatures above 260 degrees. It's not possible these days. Where to place corrosion probes? You need to place them where corrosion is expected to take place. So this is in dead fluid areas, high velocity streams, downstream of points of possible oxygen entry, locations where water is likely to collect or accumulate. When you have had already some failures, you might be interested in monitoring that area. In the case of refineries where you have amine or glycol streams, vapor sections, and glycol regenerators, and in general, areas where liquid or vapor interface occurs. I also want to share part of my experience. Sometimes we have corrosion probes installed in our assets. Here we can see one. It's easy to recognize because they have this typical small chain and a lid to cover it up. And then we can know that it's there. But sometimes we have also this type of access fitting close to another one. when there is not experienced personnel on the field trying to find it out, they might have some challenges. That's why documentation is important. That's what the message that I wanted to give with this slide. Record keeping of where exactly in our PNIDs the corrosion probe or corrosion coupon or bioprobe they are located. Because sometimes they are named in the PNID corrosion monitoring. 1, 2, or 3 access fitting, one next to the other one, and there is not clear identification of them. Where to place them? Okay, if you have several of them, you need to place them at least 30 centimeters in between, and depending on where you expect water accumulation, you want to place them at the bottom, middle, or top of the process. And this is a real life example on how to calculate corrosion rate with corrosion probes. This is where things get complicated for some operators, because what we get from the handheld device that you saw earlier in the picture is a reading that is in between 0 and 1,000. 1,000 because usually corrosion probes, the area that they have exposed is divided by 1,000 parts. So the device only says, okay, you have lost already X amount of parts, and you get the remaining part of the probe. So in 2020, we got a reading of 353, and then in 2021, we had lost 461. Then you can use the equation that is provided by the supplier of the probe, depending on the span, meaning the accuracy of the probe, if it's thick or thin. You will use a calibrating factor. And when you combine the difference between at least 2 readings, the time, and the specific characteristic of the probe, you can get corrosion rate in millimeters per year, for example. In our case, I'm very happy to say that it was very low, 0.013 millimeters per year. And to be able to do these calculations, you need to have technical information of your probe. You need to know which probe you are using to be able to fill in the span in the equation. This is an example of how we can use or interpret the corrosion probe, how to use the corrosion probes to optimize inhibitor injection. Here we can say, okay, we were injecting 5 ppm, corrosion rate was high. Then we increased the dosification to 15 ppm, and corrosion rate went lower. This is another example of how the state-of-the-art probes, they can get more accurate information quicker with less noise, electrical noise. This is my contact information. I hope that you had learned a couple of things, and if you have more questions, please ask 1 or 2, because we need some time for the next speaker, and also in the coffee break, feel free to reach out to me. Also, this presentation will be available on my YouTube channel, Corrosion. You can find me on LinkedIn and also on Instagram as Corrosion. Thank you very much. Do you have questions?
Thank you, Henry. Yep. Yep.
Thanks for the wonderful presentation. Just 3 quick comments that I've got here. The first one is around the frequency of removing the probes, and I think from operator's point of view, I would rather have a long-term probe that I can retrieve once a year than the one I'm going to retrieve every 3 months, and that's because some of those probes were installed such that you cannot retrieve them online. Mm-hmm. So it is, I don't want to say best practice, but I think it's the best advice to make sure that if you have ER probes installed, you can retrieve them without shutting down production so that you can retrieve them. So that option is available. Yeah. Then the second point I was going to make is around the possibility of having wireless transmission of data. I've seen that displayed by a vendor. So that's also possible. Yeah. And that takes away the risk of having operators who don't know how to download data from the probe. So if you have wireless transmission, you can get your real-life or real-time data. Yeah. And final comment is that always good to have a combination of ER probes and coupons as well because they give you different data. Thank you.
Yeah, fully agree with you. No comments to be added. I fully agree. Thanks for adding the extra comments.
Mark Jordan with Champion X. Just a question. What's your view of side stream ER probes, temporarily installed equipment for trials and optimization? Do they have a role to play, or are they limited by the fact that they're temporary?
Definitely. Yeah, you can use ER probes as for special projects when you want. If you don't have an access fitting, you can use them as a temporary solution to measure the corrosion rate while you are doing some trials with a corrosion inhibitor or different injection rates. And also you can, if you want to, it's not advised, especially in our business, but these probes, they are quite durable, so to say. And you can even use them for a couple of days. Let's say well number one, you do your optimization. After a couple of days or weeks, if you have the tools to do this online, you can retrieve it, close this one, go to well number two, use the same probe. If that probe matches the expected corrosion rate that I explained, you can move them. So they are quite flexible. And in some cases, you can also use them to mimic some lab test. You can use them not on site, but you can take some samples or play a little bit with a corrosion inhibitor dosification and use them in the lab. Instead of having to buy a potentiostat, galvanostat, you can use them to do some quick checks.
Hi, Martin Lee, Champion X. Just a quick question regarding, how critical or how important is the orientation of a probe in the system, and how does that vary by different types of systems?
Yeah. I already gave one example more downstream in refineries, especially in the feed. You want to make sure that you have a reading within minutes or no more than 10 hours. In my case, we don't need quick responses in the matter of hours. We can have more robust ER probes that they can last longer and give me some information because my process is quite stable. So if I understand your question correctly, you need to go case by case and ask yourself, how quickly do I need feedback? Does that answer your question? I mean, there is not a general answer to this one, but the guidelines, as I already explained in the presentation, you need to know how quickly you want to have the answer, and in some cases, how quickly you are going to take actions. Because some operators, they say, oh, I am interested in having the information as soon as possible, in a couple of minutes or hours. I will retrieve the probe every 6 weeks, no problem. And then if they need to check, for example, corrosion inhibitor or pump, they would take 2 weeks or 3 weeks to repair because you have to create a work order, maybe a third party has to come on site, and then, okay, from the process point of view, you are interested in having an immediate, very quick reaction, but in reality, it's not going to be the case, so you need to find the balance. Does that clarify? Thank you very much for the question.
Thank you very much, Henry. Thank you.
Thank you.